This is Ham College, episode 55 for July 31st, 2019. Ham College is brought to you by Icom. Make the most out of this contest season with Icom. And by hamstudy.org, a great way to study for your next license exam. Good evening. Welcome to another exciting episode of Ham College. I'm Professor Thomas.
And I'm Dean Martin.
And boy, we have some topics to cover tonight that I think will be of interest to folks.
Oh yeah, they were of interest to me.
Well, we got some explaining to do as well.
Yeah, plenty of that.
And some pictures to show and
lots of show and tell.
About the show and tell. And we're going to be testing you folks that are watching and see how you do on your general exam. We're coming close to the end of the question pool.
Yeah, very. How many? I think we got one more show, maybe. Maybe two.
Maybe 1.5. Or two.
That's going to be tough to pull off the half one.
Well, it is. And then we're going to do a follow-up. You know, the pool has just changed.
Yep.
And so we're going to, there's going to be a few questions that have been added to the pool, and we'll be covering those so that you've got everything that's been on the general test could possibly be there when you go take yours.
Yeah, that was inconsiderate of them to change that before we finished.
They could have held it off another couple of weeks, couldn't they?
I know, right?
Yeah. Oh, well.
They didn't confer with us on it.
Oh, no, they didn't, but they usually don't. What is that? Is that the chip shirt you got on there?
This is the Mississippi Institute of Technology.
They spell it funny.
It's actually Massachusetts Institute of Technology. Yeah, I went to MIT, and I bought the shirt, and then I left.
Yeah?
I bought it when we went up there on vacation.
That looks good.
To the campus.
Well, I can't say I went here, but you know, I'm all about the arts, and that's why I've got on the Music Memorial Radio Station shirt here.
That's pretty cool. Yeah, you got, who gave you that?
Kevin, ZL1KFM, when he was over visiting, you know.
I got, one of them I got was a volunteer fire department. Did you get that one?
I got that one too, and I hadn't worn it yet. I need to.
I might wear mine next time.
Need to wear it,
Yeah, that's pretty cool.
Yeah. So, thanks for that, Kevin. Chip. Chip gives you a thumbs up, sort of, on your shirt there. He says you need the K9 on that shirt. Yes, for K9 MIT.
Oh, that's true. Actually, I do.
I've got some tape here. We could probably draw that up and...
Sure.
Yeah. I think I've got some stencils and some spray paint, so during the break a little later we can...
fix it up during the intermission?
We can fix it right up. Before we talk about tonight, let's talk about last month. What did we talk about last month?
Well, so much has happened since then. But I believe it was digital components and Ohm's law. Oh, yeah, there was a lot of Ohm's law.
Yeah, and RF connectors.
Yeah.
And we looked at the different types of connectors and gave names to them.
It was a very math-intensive show last time.
Yep, it was.
We're not going to beat you up that bad this month.
No, we're not. There's just a few things you need to know, though. And once you understand these, it'll all be clear as day.
Yeah.
Yeah. So I guess we ought to get right on to it here. Oh, we want to mention anytime we're doing a show live, we've got a chat room going on at the same time. You can join in there, AmateurLogic.TV/chat. All our rowdy friends in there, they will be answering the questions as we go along tonight. And we will compare our own answers against theirs. and take the best 2 out of 3.
It's like rock, paper, scissors.
Yeah, more or less, yeah.
Yeah.
Scientific-like.
Yeah. And what I usually say is if you're not in the chat room and you're watching the live stream, you're missing half the fun. So it's up to you to figure out which half. I took your line from you.
Yeah, you did. I have nothing left to say now for the rest of the hour.
What is the RMS voltage of a sine wave with a value of 17 volts peak? A, 8.5 volts.
B, 12 volts.
C, 24 volts.
Or D, 34 volts. What is the RMS voltage of a sine wave with a value of 17 volts peak? All right, let me think about that. All right, so if it's 17 volts peak, I know the answer is going to be less than 17 volts because the RMS voltage is less than that. And you mentioned something about having a calculator earlier.
Yep.
Let's say 17
volts.
17 divided by 1.414. And I'm going to say it equals 12. 12 volts is going to be our answer.
Pretty close to 12.
Pretty close to 12. Well, let's see. Was that one of our choices here? And yeah, it's B. I'm going to say the answer is B.
I would concur with that.
Okay. Over in the chat room, they're kind of mixed there. We've got A's and B's over there. So, Chip came up with the answer a different way, but I think would give you the same answer. Let's just look at the answer here. It is 12 volts.
Mm-hmm. Yeah, that's the way I saw to do it times.
So let's just look at it that way. So if you took the peak voltage, which was 17 volts, times 0.707, would you get the same answer? Close. Pretty close. But either way will get you there.
Either way works. As long as it's a true sine wave. Now, if you've got a square wave or something,
well, if you got a square wave and I had 17 volts peak, what would be the RMS voltage?
I don't know. It wouldn't be 17. I guess it'd be half of 17. What would it be?
17.
Would it? Well, I guess it would. That's dumb. I deserve a buzzer on that.
I'm not sure that's one of the questions. You brought that up yourself, so you put it on yourself.
Yeah, that's true. I'm usually my own worst enemy anyway. First of all, RMS stands for root mean square.
So let's say you had a resistor, 100 ohm resistor, and you were going to put 12 volts DC on it.
Right.
That resistor would get to a certain temperature.
Right.
All right. So what if you were going to use AC voltage instead? If you put 12 volts on it, that was 12 volts RMS, you would get the same temperature. If we're looking at the diagram right there, the first vertical dotted line represents the voltage RMS in case you can't see it. And then the one right there, the next vertical line is voltage peak. You know, an AC waveform's like that sine wave right there. It starts at 0, sweeps up to a positive peak, then it comes back down through 0 and goes down to a negative peak, and then goes back up to 0 again, and that's one complete cycle. We'll talk more about that in a minute. It's kind of an averaging thing. In other words, if I put 12 volts DC on that resistor, that's going to be 12 volts full time. Mm-hmm. If I put 12 volts peak in there, that's only going to be a full 12 volts at the top of that waveform right there. It's not going to be 12 volts for, that whole half cycle. It's only going to be, right at the peak. So what the RMS is doing is kind of averaging that out to to give you the same power as if it was a steady DC voltage.
That's pretty interesting. It's kind
It
of
is.
stuff to get your head wrapped around it.
And I think it warrants some more questions on the subject.
Does it?
Yeah, as a matter of fact, I have one for you.
Okay, hit me with it. I may have a sneak up on it.
As long as you get there.
Okay.
What voltage of an AC signal produces the same power dissipation in a resistor as a DC voltage of the same peak? A,
The same value.
the peak-to-peak value.
B, the peak value.
C, the RMS value.
Or D, the reciprocal of the RMS value. What value of an AC signal produces the same power dissipation in a resistor as a DC voltage? Well, we basically just covered that, so that's going to be C, the RMS value.
The RMS value, well,
It's pretty much the exact same example we just discussed.
right, apparently we covered that well because everyone's getting it right in the chat room.
They all snuck up on it too.
Yeah, there really was no sneaking involved there. We had exposed it
Yeah.
before the question ever came up. But let's just verify. Yeah, you get a fist bump on that
I'll
one.
take that. What portion of the AC cycle is converted to DC by a half-wave rectifier? A, 90 degrees.
B, 180 degrees.
C, 270 degrees.
Or D, 360 degrees. What portion of the AC cycle is converted to DC by a half-wave rectifier? Okay, a half-wave rectifier is only going to rectify half of the waveform. The whole waveform is 360 degrees, so 1/2 would be 180 degrees. I'm going to say it's B. Do you concur?
I concur, Doctor.
And
I mean, Professor.
yeah, it's close enough. I'm just as much a doctor as I am a professor.
Do you have your doctorate yet?
No, I don't. Yep. But I do have my post hole diggers out here in the shed. Yeah.
There you go.
B. Everyone's saying it's B, so I feel pretty good about that answer.
Oh, yeah.
And it is. It's B. But let's do a little explaining on that and see if we can't make it a little more confusing.
Okay.
And you see that sine wave there on the left from the first time it crosses zero going up, through it crossing going down, and then it returns to zero again. That is a full cycle. That is 360 degrees. So the half-wave rectifier only puts out the top half, so that's why I say 180 degrees. What if, however, there's another type of rectifier?
That was only halfway rectifier.
That was only half of it. Let's talk about a full-wave rectifier. What portion of an AC cycle is converted to DC by a full-wave rectifier? Is it A, 90 degrees?
B, 180 degrees.
C, 270 degrees?
Or D, 360 degrees. Well, if a half wave was 180, then it's got to be 360 degrees.
So you're saying it's D.
I'm saying it's number D.
And you didn't cheat by looking in the chat room to see what everybody was saying.
I looked at the chat room after I said the D.
Okay. Everybody's got that one right. That must have been
even deans can multiply by 2.
Okay. Well, let's see. Let's see. And you got it right. 360 degrees. And I figured you would get this one right. A full-wave rectifier. Same thing as before. On the left-hand side, we see the voltage coming in. That's a sine wave. It's an AC signal. Then we've got a transformer. That transformer has a center tap on the output. On the secondary side there, we can see there's 2 diodes connected. The center tap is going to what would be ground, although it's not. There's no ground symbol there. Our resistor is fed by those two diodes right there. We're getting conduction on both halves of the waveform now. Instead of before, where the half-wave rectifier, we only had the one diode and we only got the positive peaks. Now, with the full-wave rectifier, we're getting the peak on either end of the swing, positive or negative. We've got more voltage, or more voltage more of the time. Interesting phenomenon there. Since there are twice as many positive peaks, in the case of a 60 cycle sine wave, now we've got a ripple voltage coming out of there that's 120 hertz, because we got twice as many peaks as you would have if it was 60 hertz.
Yeah, but DC.
Mm-hmm.
Yeah, that's interesting, because the example that I saw had 4 diodes. It almost went around in a square. It had a tap on it. It was kind of different. I wish I had saved the drawing.
Let me get it right now. You're saying you saw a full wave circuit that had a square.
Yeah, 4 diodes.
You know, that sounds sort of like a full wave bridge rectifier circuit.
Oh, yeah?
Yeah, like this right here.
Wow.
How convenient, right?
You're good. That's why you're the professor.
See, I was thinking ahead.
You read my mind, too. That's scaring me.
So this circuit's a little bit different. It's got 4 diodes there, and you notice there's no center tap on that transformer.
Yep.
That's why we'll often use a full wave bridge rectifier like right here. It's because all we need is a single secondary off that transformer. We don't need a center tap, and we're still getting the full use of that waveform. If I had a drawing instrument here, I could draw on that, which I don't have that set up. We could see that no matter which way that waveform is swinging, we're still getting output over to that resistor. We're getting output voltage on the positive swing and the negative swing of it. Same result as we had with the full wave rectifier, but using the bridge here. While it may look more complicated there, it's another way to do it, and you don't need a center tap transformer.
Yeah, it's really interesting if you think about that. I would have never dreamed to build something that way to get that, but I mean, that's pretty cool.
Yeah, it's not drawn out here on this page exactly the way you described it, but it is.
So happen
it's
to
wired
have
the
one
same
right
way.
here, thanks to Chip.
That is the same circuit. Basically, we were just looking at.
Just laid out a little differently.
Yeah, it doesn't have a transformer. It's just coming straight, from the oscillator, but same result there.
Yeah, so that's what I saw. Thanks, Chip.
But we got more questions, and one you kind of brought up an interesting point about earlier, but I'll let you ask me since it's your turn to ask the question.
Okay. What is the output waveform of an unfiltered full wave rectifier connected to a resistive load? A series of DC pulses at twice the frequency of the AC input.
B, a series of DC pulses at the same frequency as the AC input.
C, sine wave at half the frequency of the AC input.
Or D, a steady DC voltage. What is the output waveform of an unfiltered full wave rectifier connected to a resistive load? Well, we just looked at the output of a full wave rectifier.
We did.
And I think I made the comment that it's, the ripple is twice the frequency of the input. I'm going to say it's a series of DC pulses at twice the frequency of the AC input.
I would agree.
Everybody's got that right over in the chat room. There we go.
Cool.
A series of DC pulses at twice the frequency of the AC input.
Yeah, I mean, that makes sense.
And because it's unfiltered. Now, when we say filtered, we've probably hung a big capacitor across that resistive load, and we smooth that out more to just a straight DC. You might see a little ripple or some pulses in it, but it'll be more or less flat, like a voltage from a battery.
It makes me want to build a power supply.
You should. You should build a power supply, old school.
Yeah. But maybe I just will. As soon as I get my fire extinguisher charged up
Oh, you
from
won't
that
need
last one.
Which of the following is an advantage of a switch mode power supply as compared to a linear power supply? A. Fast switching time makes higher output voltage possible.
B. Fewer circuit components are required.
C. High frequency operation allows the use of smaller components.
Or D. All of these choices are correct. I don't think D is the answer. Faster switching time makes for higher voltage. I don't think so. Fewer circuit components. I think it's going to be C. Higher frequency operation allows use of smaller components. Because I know the switching supplies are really tiny compared to the old linear ones that I've got.
Yeah, I'm going to agree with you.
You would never get a linear supply down to the size of that.
No, not with that kind of output current.
No.
Most everybody's agreeing. There are some mixed answers in there. I'm going to go with you, though. High frequency operation allows for the use of smaller components. Let's see if both of us are right. Yep. That's what a switching power supply does, sort of. It takes the frequency that's coming in, say your 60 cycle AC, it converts that frequency up to a much higher frequency of waveform. Then the components that it uses in there, you don't need as big of filter capacitors and all as you would at a lower frequency, because the reactance is different, for the higher frequency than it would be at a lower frequency. So yeah, there's that. And as Mike says in the chat room there, yeah, switching to power supplies do require more components, certainly not less.
Because of filtration?
Just because of the whole nature of the circuit, that it takes to pull that off. So we're going to be back in just a moment, but I think right now we could use a little break. Ralph seemed like he was getting a little thirsty in there a moment ago.
Yeah, I wouldn't mind turning the air conditioner on for a few minutes.
That's kind of what I was thinking. Yeah, you're following me there. See, you could be a professor too.
Maybe
soon.
One day.
Yeah. All right, we'll be right back.
Let's all go to the lobby. Let's all go to the lobby. Let's all go to the lobby to get ourselves a treat.
Delicious things to eat.
The popcorn can't be beat. The sparkling drinks are just dandy. The chocolate bars and the candy. So let's all go to the lobby to get ourselves a treat. Let's all go to the lobby to get ourselves a treat.
Now to pause and refresh. For your convenience, we have an attractive refreshment stand in the lobby with buttered popcorn, golden good and hot from the popper, your favorite candies, wholesome and rich with a flavor treat for every taste, ice cream and other good things to eat, plus delicious Coca-Cola. So bright and bracing with the tang and tingle unmatched by any other beverage. Enjoy ice-cold Coca-Cola at our refreshment stand right now.
Are you new to the ham world or an existing amateur operator who wants to take your license to the next level? Study for your radio license exam at hamstudy.org. Hamstudy.org is a free online learning tool powered by Icom. It was created by Richard Bateman, KD7BBC, Michael Stufflebean, KV9G, and Rich Porter, KK6GKE, and it uses a modern web design to enhance the experience of studying for your technician, general, and amateur extra exams. Since 2013, hamstudy.org has helped new and existing hams to familiarize themselves with the question pools, use stats-based flashcards to focus on material they need to learn, and take practice exams to gauge progress. Visit hamstudy.org on your desktop computer or mobile device. Register for a free account at hamstudy.org to access personalized study history and other site features. Prepare for an exam in an intuitive and comprehensive manner. Check out hamstudy.org, powered by Icom, for free learning tools. Good luck on your next exam. You can ask me this one.
Okay, I will. What is the peak inverse voltage across the rectifier in a full wave bridge power supply? A, 1/4 the normal output voltage of the power supply.
B, half the normal output voltage of the power supply.
C, double the normal peak output voltage of the power supply.
Or D, equal to the normal peak output voltage of the power supply. What is the peak inverse voltage across the rectifier in a full wave bridge power supply? I haven't looked at the chat room yet, but I'm going to say we are probably going to have more than one letter guessed in there on this one.
You think?
More than one answer guessed, yeah. Is it 1/4 the normal
I'm
output
going along
voltage?
with what, so far it's the same one in there, and that's the same one I think it is too.
Is it half the normal output voltage, double the normal peak output voltage, or equal to the normal peak output voltage? What is the peak inverse voltage? I'm going to say it is C, double the normal output voltage of the power supply. Oh, chat room is saying it's D.
And that's what I would have said.
Are the rectifiers silicon rectifiers? We don't know that, Mike. Could be germaniums. Well, let's just see. We could have buzzer action right here, because everybody's saying it's D except me. And it is.
Oh, yeah.
Now, you give me a fist bump for that one?
For the buzzer. That was
Wow.
from Emil.
How did I miss that? What's worse is the next thing on the card deck here is a drawing for me to explain that.
You got some explaining to do.
I'm not sure I can. Each of those diodes there are only, the peak inverse across is only exposed to half of the waveform. First time I saw George miss one, KC5HCO said, it is not the first time. I've
No,
missed
it's
some
not
before.
the first. It's the first one of these electronic ones I think you've missed.
Could be. Maybe. Maybe not. But I'm going to try to trip you up this time.
All right. Probably won't be that hard. I'm just a dean. I spend most of my time in the hot tub.
What is the peak inverse voltage across the rectifier of a half-wave power supply? Is it A, 1/2 the normal peak output voltage of the power supply?
B, 1/2 the normal output voltage of the power supply.
C, equal to the normal output voltage of the power supply?
Or D, 2 times the normal peak output voltage of the power supply. I think it's going to, let me make sure I'm understanding this right, because I don't see the one that I would have thought. What is the peak inverse voltage across the rectifier in a half-wave power supply? The peak inverse voltage. 1/2 the normal peak output. I don't think it's half. Equal to the normal output voltage. I think it's C. I think it's going to be the same peak voltage. It's just going to be spaces in it, or ripples in it. At least that's what I think.
They're kind of mixed in the chat room on that one. So,
Did that make sense, what I just said?
well, let's see.
Nope. 2 times.
Back-to-back buzzers.
Yeah,
I don't
you
know
wanna-
that that's ever. Yeah, I'll
2 times
I'll tap that
normal
thing.
2 times.
Yeah,
I don't understand that one.
I do. And I understand why I missed my other one.
Because you thought it was this one?
Because I thought it was this one, yeah. Let's just do some explaining on this one since I knew what the answer was on this one. The peak inverse voltage would be what's the maximum voltage that diode could see. The peak output voltage is on the right hand side. It goes from the zero line up to the positive peak.
Mm-hmm.
All right, that's the peak output voltage. But that diode is seeing the whole waveform. It is seeing the positive and the negative peaks. So it is seeing 2 times the peak output voltage. It's not conducting both halves of that waveform.
Oh, I see.
But it sees
I
both
misunderstood
halves.
the question.
Yeah.
I didn't understand exactly. I get it now.
That's what happened to me a while ago. I didn't understand the question.
So it's seeing the whole 360 degrees.
That's it. Yeah. It's seeing the whole waveform is
So
across
from
that diode.
So say 10 positive and 10 negative,
Right. Yeah.
which would be 20. So
Yeah.
I get it now. That's,
Okay.
I just didn't understand.
And in the full wave bridge, that diode wouldn't have seen both halves of the cycle.
Right.
So that's why I missed that one, because I was thinking about it wrong.
Well, you're the professor. I was trying to learn from you.
Well, I know I led bad example there, but if I jumped off a bridge, would you?
I don't know.
That's a good answer. Good answer. I like that answer.
Depends on what's down there,
Okay.
how high it is.
All right. You can ask me this one.
Okay.
Now, we're already at the maximum buzzer limit per episode,
Okay.
so we can't miss anymore.
Which of the following components are used in a power supply filter network? A, diodes.
B, transformers and transducers.
C, quartz crystals.
D, capacitors and inductors. Which of the following components are used in a power supply filter network? Well, the filter network is going to try to filter out that ripple that is left on there. That is a frequency component. And diodes, they really aren't frequency sensitive so much, and transformers and transducers aren't. And quartz crystals, while they oscillate at a particular frequency, they don't filter at a low frequency like a power supply would need. Capacitors and inductors, if you tear open a power supply, that's what you're going to see in there is capacitors and inductors in the filter output network, or the output filter network. See, I was approaching it backwards too.
Sometimes you just got to sneak up on them.
So, what have we got? We got D's over in the chat room. That's my answer. And we all got that one right.
Yeah, that's the one I would have chosen as well.
What will you choose on this one? Why is the polarity of applied voltage is important for polarized capacitors? A, incorrect polarity can cause the capacitor to short circuit.
B, reverse voltages can destroy the dielectric layer of an electrolytic capacitor.
C, the capacitor could overheat and explode.
D, all of these choices are correct. The polarity of applied voltage is important for polarized capacitors. Incorrect polarity can cause the capacitor to short circuit. I could see that happening. Reverse voltages can destroy the dielectric layer. I've never built a capacitor, but I'm pretty sure that seems plausible as well. The capacitor could overheat and explode. I've actually seen some of those pop. So, D, all these are correct. Oh, I'm pretty sure A and C can happen. D or B, probably. Well, if it's going to explode, I'm sure it's going to destroy that too. So I'm thinking it's D. All of these are correct.
Well, that's what everybody in the chat room is saying, and that's what I'm saying too. So, There you go. You said you've seen it, a capacitor overheat and explode.
Well, I've had some pop before.
Have you seen it when it happened, or you just had one that was popped?
No, I've had one in something I was doing where I put too much voltage on it.
And it popped right in front of you?
Yeah.
That's an awesome sight, isn't it?
Yeah. Well, back when I used to do AC stuff, I didn't do anything to it. I guess they just shorted, but I remember some of those big canister capacitors blowing and the oil just going everywhere and catching on fire.
Yeah. Ooh, flammable. Yeah. Yeah, the liquid in a lot of those is flammable these days. They used to use PCB liquid in those because it was a good insulator and, did good at absorbing the heat, and it wasn't flammable. And they found out it caused cancer, so they quit using that.
Oh, great. I've probably breathed that stuff in and everything.
Oh, yeah. Me too. I probably cleaned it up where it leaked out in transmitters.
Yeah.
Okay. Well, next question.
Which of the following is an advantage of an electrolytic capacitor? A, tight tolerance.
B, much less leakage than other types.
C, high capacitance for a given volume.
Or D, inexpensive RF capacitors. Which of the following is an advantage of electrolytic capacitors? I'm going to start at the bottom. Electrolytic capacitors are not RF capacitors. They don't work up in the RF frequency range. C, high capacitance for a given volume. I think that's the answer, but let's look at the others. B, much less leakage than other types. No, electrolytics can be fairly leaky. And A, tight tolerances. No, electrolytics, the tolerance can vary on them. Doesn't matter that much if it varies a little, but they're not super tight. So I'm going to say, yeah, it's C, high capacitance for a given volume. Everyone in the chat room is saying C. What do you say, Dean?
C, Charlie, because everybody in the chat room says.
There you go. C, Charlie. What useful feature does a power supply bleeder resistor provide? A, it acts as a fuse for excess voltage.
B, it ensures that the filter capacitors are discharged when power is removed.
C, it removes the shock hazards from the induction coils.
D, it eliminates ground loop current. Bleeder resistor. That's a curse deterrent.
Curse deterrent?
Saying foul language. So I think it's going to be B, ensures the filter capacitors are discharged when the power is removed, so you don't curse if you touch it.
Okay, I see where you're going with that answer. Everybody over in the chat room is saying that. Yeah, I believe you're right there.
It's a curse filter.
Yep. Or a death preventer.
That too.
Yep. The broadcast transmitters I work in have huge, like ceramic resistors that are like, this big around and about this long in there to bleed off that voltage.
Oh, wow.
When you turn off the plate supply on the transmitter, those are there so that voltage bleeds down. Sometimes those things will go bad. They'll open up and there's still high voltage in that capacitor. Really,
the resistor will go bad?
Yeah, the resistor will go bad.
Wow.
And that capacitor won't discharge. And kind of a clue to it on these tube type transmitters, all of them have got plate voltage and plate current meters. If you turn off the plate voltage and you notice that plate voltage meter is just slowly going down, that's a hint that bleeder's not working.
Oh, yeah.
It's open. And I have seen that happen.
You replace them?
Huh?
You replace them?
Oh, yeah. Yeah. That's why you use the Jesus stick, or as Chip coined the phrase for Bob's pine board project, the chip stick. Well, Bob called it the chip stick, but it's It's a shorting rod.
Uh-huh.
You know, you just touch it across there. After you've turned off the voltage, if you don't, the tip will be missing on the end of that stick henceforth.
Other than it's called kindling.
Yeah. So, that's a safety in case that, you know, the bleeder resistor didn't get it all. We're going to come back with more in just a moment, so don't go away.
I'm not going anywhere.
Heard it, worked it, logged it. It's time to get the transceiver that's best suited for your lifestyle. Icom offers a variety of high-performance and innovative products. Make the most out of contest season with one of these Icoms today. IC7610, the SDR every ham wants. This high-performance SDR has the ability to pick out the faintest of signals, even in the presence of stronger adjacent signals. The Icom IC7610 is a direct sampling, software-defined radio that will change the world's definition of a SDR transceiver. RF direct sampling, 110 RMDR, independent dual receivers, and dual digicell. Or get the IC7300. Changing the way entry-level HF is designed, this high-performance, innovative HF transceiver with a compact design will far exceed your expectations. RF direct sampling, 15 discrete bandpass filters, large 4.3-inch color touchscreen, real-time spectrum scope, and SD memory card slot. Keep your competitive edge with faster processors, higher input gain, higher display resolution, and a cleaner signal. Icom's IC7851 is the pinnacle of HF perfection. Dual receivers, digital IF filters, memory keyer, digital voice recorder, high-resolution spectrum waterfall display, enhanced PC connectivity, and SD memory card slot. Visit IcomAmerica.com/amateur for more information on all the great Icom radios. And thanks, Icom, for supporting the university here. You know, it would be hard to do it without their help. Boy, it just got dark in here. That's what it would look like if we didn't have their support. We couldn't afford the lights.
Yeah,
No.
that's true.
Or the radio gear.
I appreciate them and MFJ.
I do, yeah. Although MFJ doesn't support this particular show.
Yeah.
They support AmateurLogic, and a big help there. Well, you know, it's usually at this point in the show that we have something to give away, and I noticed miraculously...
Hey, I found this. Why don't we give this away?
What is that?
Well, it's a pretty cool Icom ball cap I just found.
Yeah?
And then this nice Icom Ham Crew t-shirt. I think you got one of these too, don't you? I got one.
Yeah.
But we got this spare one here. We need to give it away to somebody. Some lucky person. You'll look good at the Ham Fest coming and going. It's got the same thing on the front and the back.
Yeah. Yeah, I need you to stall a little bit longer.
It's a pretty nice t-shirt. I got mine. I almost wore mine tonight, but I thought I saw this one. I don't think I wore the MIT one on the show yet. So if somebody wanted to enter the contest to win this,
what could they do?
They could send an email. You don't have to have a license or anything. All you've got to have is a name and an email address. So send your email to hamcollege@AmateurLogic.TV and just give us your name, and the Icom people will be in touch with you pretty soon. Very soon. So, good chance when the package, they send out your shirt and your cap, they'll put some extra goodies in there. Most of the time they do.
A little longer?
A little longer?
Yeah.
Okay, I'm going to start busting out into song here in just a few minutes.
I'll hurry.
A whole lot longer. If you did enter the contest and you didn't win, we clear out the email queue every time, so go ahead and send your entry in again for next month, and there's a good chance you know, every month you enter, there's a better chance you can win. It makes sense, right?
That does make sense.
That's Dean math right there.
You know, that stuff is pretty important when you're sitting in the hot tub and you're playing poker.
I know.
You know.
Well, you want a t-shirt to put on when you get out, too.
Yeah. Yep. and a hat to impress the chicks with. So, yeah.
Heck yeah.
So, we have a lucky winner that I just drew. I know nobody noticed, but I drew it right here live on the show.
That's amazing.
Yeah, it is. Kind of surprised me a little bit. It is Stace Cunningham, W5HKR, and Stace said, I'd like to enter to win the free Icom hat and t-shirt. As far as Icom goes, I own an IC7000. Way to go. IC7300, an ID51A Plus, and a ID51A Plus 2. Oh, and also I have an ICR3 that I almost forgot about.
Cool.
So he has heard of Icom before.
He has. He's very, very familiar with Icom.
All right. Well,
So he needs a
congratulations,
shirt to wear
Stace.
while he's using all that gear.
He does. And the hat, too.
And a hat.
With that many radios.
Heck yeah.
Every one of them sounds like a winner to me, too.
So congratulations.
I have the 7000 and we both have the ID 51As.
Yeah, and I've got a plus 2 also.
I have the 50th anniversary edition, but we don't have an IC 7300. We have used them though.
Yeah, I would like one of those ICR3s, a little receiver.
I would
Nice.
too. Yeah, very portable too. You've got a good Icom receiver, don't you?
Yeah, just can't take it on the airplane with me.
They won't let you take that?
Well, they'll let me take it, but I don't want to have to. It'll take. Actually, it's not that big. I could take it if I wanted to. It'd just be a little more effort than a pocket-sized one.
Yeah.
If you didn't win, go ahead. The email's queue's cleared out, so go ahead and send your entry again for next month, and hopefully you have. Hopefully your name will be the one that's called.
Yeah, I just deleted all the entries right then, so it's a clean and open slate. Your chances are very good right now.
Hit it.
Okay, the next question. I don't remember who asked the last question. Who asked the last question?
I don't remember. It doesn't matter.
Yeah, you can ask me this one.
Okay. What precautions should you take whenever you make adjustments or repairs to an antenna? A. Ensure that you and the antenna structure are grounded.
B. Turn off the transmitter and disconnect the feed line.
C. Wear a radiation badge.
Or D. All of these choices are correct. What precautions should you take whenever you make adjustments or repairs to an antenna? A. Ensure you and the antenna structure are grounded. Honestly, I don't know that it's practical to do that. If you're on a tower that's floating, it's not. And if you're at the top of the antenna, it's going to kind of be hard for you to ground yourself without jumping off.
Floating antenna towers.
Some maybe, yeah. Most AM stations have floating antenna towers. They're sitting on insulators. Turn off the transmitter and disconnect the feed line. That sounds like a pretty good idea. C. Wear a radiation badge. Well,
or bring a Geiger counter.
Yeah, we're not too concerned with nuclear radiation here, so I don't think we need the radiation badge. So it's not D. All of these choices are correct. It's going to be turn off the transmitter and disconnect the antenna feed. B.
That's pretty much the common sense answer there.
Everybody's got a lot of common sense in the chat room here then, because everybody said it was B. It's B.
Cool.
What should be done by any person preparing to climb a tower that supports electrically powered devices? A. Notify the electric company that a person will be working on the tower.
B. Make sure all circuits that supply power to the tower are locked out and tagged.
C. Unground the base of the tower.
D. All these choices are correct. No, all those are not correct. Notify the electric company. You don't have to notify the electric company.
They'd be happy to hear from you, I'm sure.
Yeah, just tell them hi. You don't need to unground the base of the tower. The answer is going to be B. Make sure all circuits that supply power to the tower are locked out and tagged. And that means this is like a big deal where I work.
Mm-hmm.
And there's a big, they call it LOTO, Lockout Tagout.
Mm-hmm.
So anyway, we go ahead and see what the answer is.
That's what everybody said over in the chat room. Yeah. What does lockout tagout mean?
That means lock where you can turn the power on and off. All the stuff out there's got a latch on it, and you put that in there. You've got a lock with the color and your name on there, and you lock it and keep the key with you so nobody can accidentally go in and turn it on. Or
you put a tag on it.
Yeah. Well, they do both.
Yeah, well, it's better to, yeah.
Yeah.
Yeah, lockout, tagout. That became law a number of years back here.
Did it?
Yeah, I think so.
Well, it's the law where I work. If you don't do it, that's one of the few things that'll get you on the road.
Yeah.
Really fast.
Okay.
And it should. Mm-hmm. Which of these choices should be observed when climbing a tower using a safety belt or harness? A. Never lean back and rely on the belt alone to support your weight.
C. Confirm that the belt is rated for the weight of the climber and that it is within its allowable service life.
C. Ensure that all the tools are securely fastened to the belt D-ring.
Or D. All of these choices are correct. Let's see.
We got a mixed bag here in the chat room.
Which of these choices should be observed when climbing a tower using a safety belt or harness? Never lean back and rely on the belt alone to support your weight. That is a good idea. That used to not be the case because everybody used to lean back on the belt except me. I wouldn't do that. B. Confirm that the belt is rated for the weight of the climber and that is within its allowable service life. That sounds like a very good idea. C. Ensure that all heavy tools are securely fastened to the belt D-ring. And while I don't recall necessarily seeing that, that does sound like a good idea.
It does seem like a good idea.
I know.
Especially if somebody's down there.
Yep. I know that, yeah, it is. I know the first two, and the third one sounds like a very good idea as well. So I'm going to say it's D. All of these choices are correct. And you said there were some mixes.
Well, I thought I saw a B at the beginning.
Yeah, I see a couple of B's in there. Well, let's see. And the answer is B. Confirm that the belt is rated for the weight of the climber and that it's within the allowable service life.
That's funny to me because I would have thought it would have been D because it doesn't seem like you'd want to leave all your weight on that one belt.
Yeah, I bet a lot of people would think that it was
And C.
D.
Ensure that your tools are securely fastened to the belt's D-ring. That seems like a pretty good idea as well.
Yeah, but I question that. Now, let me just say that everybody in the chat room, almost, a lot of them guessed D on this one.
Yeah.
There were a couple of B's.
I could see where they could do that.
It is a trick question. Never lean back and rely on the belt alone to support your weight. They want you to be double connected to the tower. But anyway, in this case, the answer is B. I'm not going to get into a lot of discussion here about proper safety on a tower other than to say before you climb or let anybody else do it, you need to research it. It's not something to be taken lightly because it's very, very dangerous. We've lost a lot of hams in recent years. Well, we've always lost a lot of hams because of that, but just in the last few months, we've lost some.
Yeah, safety's nothing to laugh at anyway. I mean,
not like
take
that.
It all very serious.
Yeah, there's only one mistake on that, So follow all the precautions and research before you actually do a project like that. Tommy, I know nobody in the chat room could guess what we're going to talk about. What if you hadn't been to the Massachusetts Institute of Technology, or didn't have a buddy affiliated with the Music Memorial radio station, and you didn't win the contest.
Well, if you didn't win the contest, you can enter again, so I suggest you do.
Yep.
For one thing.
Yep.
But if you're in a really hurry and needed a shirt.
In a tight spot.
If you're in a tight spot, you need a shirt or maybe something else.
Yeah.
You know, there could be some other things in there.
And there's a place that you can find such items online.
It's like magic. You go in there and pick what you want.
Yeah.
Put some numbers in the screen. You can go to AmateurLogic.spreadshirt.com and get all kind of swag. And there's some new stuff in here based on some input from you guys out in the chat room and emails. We've got a Ham College Volunteer Examiner shirt now in multiple colors and sizes. We've got Ham College and Amateur Logic backpacks, computer backpacks.
That's what all the kids will be wearing at college this
year. Green transparent one that changes
oh, that one.
At your altitude.
Or not.
Or not.
Oh, that's the Anode Rules.
We've got the Anode Rules Ham College shirts, which is a spin-off of this actually came from some comments in the chat room. I think Mike VE3MIC may have started that one. Yeah,
well, Anodes, that is the official team name of the college, the Fighting Anodes.
Yeah.
And the Anode comment came from that time that we were doing a demonstration. I was a cathode.
Yeah.
And you were an anode.
Yeah. So anyway, the anodes rule, man.
Yep.
So anyway, these are out there now.
I got to have that.
We've got Anode Rules ball caps, if you prefer that. We've got coffee mugs now. This particular one has a logo on both sides. It's Amateur Logic on one side, Ham College on the other.
I got to have one for each hand.
And we've got the Amateur Logic brain logos that you've seen us wearing the shirts on for so long, and we finally got those on here for sale. A lot of you have asked where you can get them. Well, there they are.
And that took a lot of doing.
We got some polos. It really did. We've got the regular Ham College logos, similar to the sweatshirts that Mike and Mrs. E3MIC sent us, except they don't have the call signs on the back. We've got hoodies, sweatshirts, the other Amateur Logic logo T-shirts and sweatshirts and everything, jackets. There's a lot of new stuff out there, so go take a look at it and see if it's something you like.
That's some good stuff there. I like.
Yeah, I kind of like the VE shirts. I'm gonna get one of those myself. I think I'm gonna get one of those coffee mugs with the two logos, the logo on each side.
Yeah.
The Amateur Logic and Ham College on there, and maybe one of the backpacks.
Yeah, I like the looks of the backpacks too. Like I was trying to say, that's all the kids will want that when they go back to college here in a few weeks.
Yeah, great going back to school gifts.
Yeah, and the Amateur Logic would make a great field day accessory.
Absolutely.
And the coffee mug would work great right here on the table. I'm gonna have to get that.
Yeah, I'm gonna order one.
Yep.
So anyway, hope you guys like those, and you can find those at AmateurLogic.spreadshirt.com.
Yep. Well, before we get out of here, there's a few other things that we want to mention. Where you can catch up with us during the month, because we're not always here streaming live.
Oh, really?
Yeah. At least I'm not.
No.
I don't recall seeing you back here either, so. You can catch up with us on Facebook.com/group/Ham College if you do the Facebook thing.
We're on Twitter at Ham College, and we also have at Amateur Logic. And do you want the next one?
And the new addition here is the one that you've been asking for, the groups.io/G/AmateurLogic group, or community. What do they call it? I guess they call it a group, huh?
Yeah, Yeah, so if you don't do the typical social media things, this one you can log into the website if you want to, or you can just subscribe and reply via email. And it's really good. Like I said before, I was a little bit skeptical about it, but it turned out I really like it. You get, if you have your email settings on there set to send individual emails, you'll get an email shortly before the show starts. So if you check your email on your phone, you'll know when we're going live.
Yep. Well, I did notice that there's some requests for AmateurLogic towels in the chat room there. The cooling towels would be nice.
Oh, that would be nice.
I don't know that I've ever seen those personalized.
I don't remember seeing those in the Spreadshirt thing, but I'll have to go look and see what else is in there. They have a lot of products. I got on a spree, I guess it was last weekend, and I just started making. I was sewing shirts and backpacks and stuff till my hands were bleeding.
The show notes, you can find those at AmateurLogic.TV/wiki. The show notes for both AmateurLogic and Ham College right there.
Yeah, thanks to Dan for doing those.
Thanks to Dan. It's a little behind right now. He's at the Oshkosh Air Show, and he told me as soon as he gets home, he's going to be updating those. Okay. So thanks for that, Dan. And I guess that's it. I guess that's it for tonight.
Okay. Well, let's turn the air conditioner back on.
That sounds like an excellent idea to me. Thanks for being here, everyone. Join us in the middle of next month for the next AmateurLogic and the end of next month for the next Ham College.
Yep. Almost the end of the general series. We'll see how the question pool ends up. So.
Yeah, we don't have many episodes left on general.
So, 73, everybody. We'll see you next time.
7-3. And the answer is B. Confirm that the belt is radiated for the weight of the climber. Radiated.
C. Excuse my voice. I hit puberty. C. Double.
Push your magic button here and see if that helps.
C. Ensure that all heavy tools are secretly.
It's requesting AmateurLogic toilet paper. You'll have to make your own.
Yeah, you have to make your own. We've got some of the crime scene. We got some of the crime scene tape.
Go for the D. Martin look, the face there.